Okay, so for our last physics test, we had this problem, and it was electrons are being fired at the Starship Enterprise by a Romulan spaceship. Data calculates the velocity of the electrons to be a vector with 0.8 times the speed of light in the x direction, 0.5 times the speed of light in the y direction, and 0 in the z direction, where c is the speed of light. What is the magnitude of the momentum for one of these electrons? Okay, so in order to calculate the magnitude of the momentum, you need to find the magnitude of the velocity vector here. So in order to find the magnitude of this vector, the magnitude of the velocity is equal to the square root of each of these components squared. Plus 0 squared. And c here, c is the speed of light, which is 3 times 10 to the 8 meters per second. So when you multiply that out, you end up getting the square root of 0.89 times the speed of light squared, which is the same as 0.94 times the speed of light. Okay, so after you have that, you can find the magnitude of the momentum. And in this case, since they're moving so close to the speed of light, at 0.94 the speed of light, we're going to have to consider the relativistic model. So in this case, the momentum is equal to gamma times mass times the velocity. Alright, so the equation to solve for gamma is 1 over the square root of 1 minus the magnitude of the velocity over c all squared. Alright, when you plug into the equation, you're going to get 1 over the square root of 1 minus 0.94 c over c squared. So the c's are actually going to cancel out, so it's just going to end up being 1 over the square root of 1 minus 0.94 squared. Okay, so when you actually solve it out, you get 1 over 1 minus 0.89, which is equal to 1 over the square root of 0.11, and that's 3.0151. So after you have the value for gamma, you can go back into this equation to find the magnitude of the momentum. Okay, so the magnitude of the momentum is equal to gamma, which we just found, 3.0151, times the mass of the electron, which is 9 times 10 to the negative 31, times the velocity of the electron, which we found the magnitude of the velocity is up here, which is 0.94 times c, and c is 3 times 10 to the 8th. So when you multiply all of this out, you get the magnitude of the momentum, and that ends up being 7.65 times 10 to the negative 22nd kilograms per meter second. Kilograms times meters per second. So that's the momentum of the electron. Now moving on to the second part of the problem. The second part states Captain Picard wants to reverse the electrons back to the Romulan spaceship. He orders Worf to fire a force field for 2 seconds that reflects the electrons back along their original path. If the magnitude of the electron's momentum is unchanged, evaluate the net force, the force vector of the force that is field applied by Worf. Okay, so in this case, the important pieces of information is that the time of the burst is for 2 seconds, and that the electrons are getting reflected back on their original path. So you can know the momentum principle, and the momentum principle is that the change in momentum is equal to the net force applied times the amount of time that that force was applied for. So the change in momentum is actually the final momentum minus the initial momentum. So since you know that the final momentum is just equal to the negative of the initial momentum, since the electron is getting reflected back along its original path, you know that the final momentum is just the negative of the initial momentum. So once we plug that in, you know that you plug in negative p initial for p final into this equation, and you get negative 2 times the initial momentum is equal to the net force times the change in time. Okay, so to solve for the force of the field that's going to be applied, you're going to just divide both sides by delta c, so you get the net force is equal to negative 2 times the initial momentum divided by the time. And you know that the initial momentum can be calculated using gamma times mass times the initial velocity, which was given to us in the beginning of the problem to be 0.8 c, 0.5 c, and 0. So over here we're going to plug in all of the values we know. So it's negative 2 times gamma, which we found to be 3.0151, times the mass of an electron, which is 9 times 10 to the negative 31st. And then you're going to multiply that by the velocity vector. I'm just going to insert it over here because I ran out of space. 0.8 c times 0.5 c times 0. And then this is all going to be divided by the time, which was 2 seconds. So once we actually solve for that, you're going to find that the net force is equal to negative 6.48 10 to the negative 2, negative 4.065 times 10 to the negative 22, and 0 newtons. And that is the solution to your problem, and you want to make sure that this is a vector, and that's the net force.